Today I'll be discussing kinematic equations. These equations will be a powerful tool that we will use throughout the semester, so it's important that we have a good understanding of how to use them. We've already learned one kinematic equation, so I'll quickly review how we derived it. This is a velocity time graph of an object moving with a constant acceleration. If we look at the velocity of the object at two different points in time, we can label them as initial velocity and final velocity. If we wanted to determine the average velocity over this time interval, we would add the two values and divide by 2, just like we would if we wanted to find the average of any two numbers. So, with uniform or constant acceleration, the average velocity is equal to the sum of the initial and final velocities divided by 2. We have also learned previously that the average velocity is equal to the displacement divided by the time. Since both of these values equal the average velocity, they must also equal each other as well. We can solve this equation for delta x by multiplying both sides by delta t. And then we can change the divide by 2 to multiplying by 1/2. That just gets it all on a single line. This is the first kinematic equation. Let's take a closer look at that equation. It has 4 variables in it. Delta x, or delta y, the displacement, final velocity, v sub f, also initial velocity, v sub I, and finally delta t, the time. If we know the final velocity, the initial velocity, and the time, we can plug them in to get the displacement that occurs. But in fact, if we know any of those 3 variables, we should be able to get the 4th value mathematically. Let's look at an example. A car enters the freeway with a speed of 6.6 meters per second and accelerates uniformly to 23.8 meters per second while it drives 3,200 meters. How long did it take to drive this far? First thing we need to do is make sure we understand the problem. A car is pulling onto a highway at a low speed and it needs to speed up. And it takes a certain distance before it reaches its final speed. What they're asking us to find here is how long does it take? That's delta t, the time. We also need to figure out which information is given to us. I see 6.6 meters per second. The unit is meters per second, and I know that that's the unit for velocity. So this has to be a velocity. This is the velocity that the car starts out at when it first gets on the freeway. So that's its initial velocity, vi. I also see 23.8 meters per second. Again, meters per second, it must be a velocity. And that's the final velocity because that's how fast it's going after it drives 3,200 meters. So we label that vf. And then finally, 3,200 meters. Meters is the unit for displacement or position. In this case, it's displacement because that's the difference between where it started and where it ended up. Delta x. Now let's set up the equation box. The first box gets what we're looking for, delta t. And in the second box, we put all of our given information. So we know that delta x is 3,200 meters, vi is 6.6 meters per second, and vf is 23.8 meters per second. We're going to use our displacement with constant acceleration equation. Delta x equals 1/2 vf plus vi times delta t. Now we need to plug our numbers into that equation. Delta x is 3,200, vf is 23.8, vi is 6.6, and we're looking for delta t, so we're just going to leave that alone right now. Now our object is to get delta t all by itself on one side of the equation. I'm going to do inside the parentheses first. 23.8 plus 6.6 is 30.4. Now I can multiply that 30.4 times 1/2 and get 15.2. All that's left to get delta t by itself is to divide both sides by 15.2. 3,200 divided by 15.2 equals 211 seconds. That's our answer for delta t. and the final box gets the answer. We'll have a lot of problems to solve in this class. Throughout the semester, we'll be using our kinematic equations to solve problems. All of the problems will be different, but they all work very similarly. We have 5 variables that we've looked at. Displacement, which can be delta x or delta y, final velocity, initial velocity, acceleration, and time, delta t. Notice for the acceleration, I've taken away the AVG subscript. All of our accelerations are going to be constant in this class, so we don't need to talk about average acceleration. It's just going to be A, the acceleration. Every problem that we have will contain 4 of these 5 variables. One of them will be what we're looking for, and then we'll be given 3 of the other variables. There are 4 main kinematic equations. The first one you should recognize. Delta x equals 1/2 vi plus vf times delta t. The next one is the final velocity equals the initial velocity plus acceleration times time. Third, we have displacement equals the initial velocity times the time plus 1/2 the acceleration times the square of time. Finally, we have the final velocity squared equals the initial velocity squared plus 2 times the acceleration times the displacement. If you look carefully, each of these equations is missing one of the 5 variables. For instance, in the first equation, delta x equals 1/2 vi plus vf times delta t. Notice there is no acceleration in this equation. The second equation doesn't have displacement. The third equation doesn't have final velocity. And finally, the last equation is missing time. The key to knowing which equation to use for a given problem is to determine which variable is not part of that problem. Like I said, we'll be looking for one variable, and 3 others will be given in the problem. That's 4 variables total. 1 is not part of the problem. You may have noticed that there's no equation that does not have initial velocity. The initial velocity will always be given, or it will be what you're solving for, or the object will start from rest. And if that happens, it makes things easier. When an object starts at rest, its VI is 0. If you look at the first kinematic equation, if you set VI to 0, then inside the parentheses you have 0 plus VF, which is just equal to final velocity. That makes the equation delta x, displacement, equals 1/2 the final velocity times the time. It's a little bit simpler. You can do the same with the other 3 equations. So, if your initial velocity is 0, it makes the equation simpler. Let's try an example. This is the killer penny. The height of the roof of the Empire State Building is 381 meters. There is an urban legend that a penny dropped off of the Empire State Building will embed itself in the sidewalk, or maybe a pedestrian's head. If the acceleration due to gravity is about -10 meters per second squared, what would the velocity of a dropped penny be when it lands? Okay, we have read the problem. Let's make sure we understand what's happening here. Somebody is climbing to the top of the Empire State Building, and apparently they have no regard for the human life below. They take a penny and drop it off of the observation deck at the top of the Empire State Building. As the penny falls, it gains speed. The acceleration is -10 meters per second squared. Remember, that negative sign just talks about the direction, so it's accelerating downwards. The question asks, what would the velocity of a dropped penny be when it lands? So they want us to find the velocity the instant before it lands. That means that this is the final velocity. What other information is there? 381 meters. That's the height of the Empire State Building. You might be thinking that that is your displacement. You would be wrong. First of all, I'm going to use delta y for displacement because we're talking about up and down movement as opposed to the horizontal movement that we would use for delta x. The initial height, the penny starts out at 381 meters. The final height is 0 meters. The penny goes all the way to the ground. Remember, displacement is the final minus the initial. So 0 minus 381 gives us a displacement of negative 381 meters. Next, I see negative 10 meters per second squared. Meters per second squared is the unit for acceleration. So that is going to be our A. At this point, I only see two givens, but we need three to decide which equation we're going to use. There aren't any more numbers, but there is a key here. Notice that the penny is dropped off of the Empire State Building. When you drop something, the instant you let it go, it's not moving at that point. It's only after you let go that it begins to fall. So if something is dropped, that means its initial velocity is 0 meters per second. So let's review this problem. We have displacement, delta y. We have initial velocity. We have acceleration. We have final velocity. That is 4 of the 5 variables. Which variable is missing? This problem does not involve time. There's no delta t as part of this problem. In that case, I'm going to choose the equation that doesn't have delta t in it. When I look, it is vf squared equals vi squared plus 2a times the displacement, in this case delta y. I'll leave it for you to solve the problem, and when you do solve the problem, show me the evidence, and that is your assignment for this video.